Alright, so here we're going to look at, continue our talk on Unit 4, right, systems of particles and their momentum. So we're going to focus on turn our conversations to conservation of linear momentum. So one thing to remember, as stated earlier, linear momentum is one of the three quantities in physics, right, or in mechanics that is conserved. Again, the other two are mechanical energy and angular momentum. Unit 5, Unit 3. Okay, so we've already talked about mechanical energy, and then when we bring in Unit 5, we'll talk about angular momentum. Now, so what happens is, right, there are two conditions under which linear momentum is conserved. One focuses around the system, the other focuses around external forces. Okay, so the first thing you're going to need to do is to identify the system. Right, and so in this video we're gonna kind of really talk about. So I'm gonna break up this topic of conservation of momentum into multiple videos because this is going to be a very long video, especially with some of the example problems. They end up being they could end up being long, and so we're going to break this up. So in this video we're going to look at systems, right? We're going to look how systems apply to momentum, and then we're going to talk about collisions and then explosions. And then we're going to talk about two-dimensional conservation momentum, and then we're going to talk about ballistic pendulums. Okay, so now a couple things. Again, the system for the AP test is really up to. There's really two things. One, if the system is not stated, then it's up to you to identify the system. Right, and so AP says if we don't identify the system for you, you have to do that, and we're going to grade you accordingly. Okay, now if the system is stated, then you cannot change or alter that system. So if it tells you that it's like the moon-earth system, you can't change it to be the earth or the moon, right? They're looking at the moon and the earth together. Okay, so that's the first condition, is you need to identify the system. The second condition is that conservation momentum occurs when there's no net external force acting on it, right, or on the system, right? And so we've talked about these a lot. An external force is something outside the system when it pushes or pulls something inside the system, okay? And then an internal force is forces that occur between objects inside the system. So again, if you identify the system as like moon earth, any effect of like gravity would be internal now. But if you just say, okay, it's the moon, which means Earth's gravitational pull would be an external force, which means it's going to pull the moon towards the earth. Okay, so momentum is conserved as long as the system is isolated. And so an isolated system, right, is one in which there are no net external forces acting on that system. And so the mathematical representation of conservational momentum is P before equals P after. So the total momentum before equals the total momentum after, which if you want to expand it would be like M1 V1 initial plus M2 V2 initial plus dot 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 equals M1 V1 final plus M2 V2 final plus dot dot dot, right? So all objects in the system are contributing to the momentum, right? And so just here's a quick example, talking about a ball is dropped and falls towards the earth, right? Is linear momentum conserved? And explain. Now, there's a reason why there's two boxes to this chart, because really there's two answers to this, right? So notice that they didn't tell us what the system was. So what we have to do is we have to identify what the system is. We know we have two objects. We have the ball and we have the earth, Okay? Now, here's the two potential answers. If I say the ball is my system, right? The only force that is acting on the ball is the gravitational pull to Earth. But what happens is, because the Earth sits outside of the ball system, gravity is external to my system, or to the system, right? Because the system is the ball only. And so if that happens, the system's velocity, right, or gravity, is going to increase the velocity of the system, which means momentum is not conserved. Right? And the important idea is right here, is because it's because the gravity is external to the system. The important idea is that it will increase the velocity of my system, which is the ball only, right? Causing the momentum to not be conserved. And you can do a quick calculation, right, by bringing in, m times v, right? So your initial velocity or your initial momentum would be 0. Well, you can easily see that, it's going to increase the system, right, or increase the velocity. The second scenario would be, now if I say, okay, the ball and the Earth, right, is my system. And so what happens is, and if I just show you in the picture, right, so the black circle represents my system. Now note that what happens to gravity? Gravity is now internal, right, to my system, right, which means there's no push or pull coming from the outside, which means the system's velocity remains constant, which means momentum is conserved. Right? And I'll put an exclamation point if I can get it nice and neat in there. Right? And so momentum is conserved. Boom. Right? Because now gravity is no longer external. Right? Gravity is now internal. Right? It's inside my circle. Right? So here, gravity is outside. Here, gravity is inside my circle, right? And so that's the way you can think about isolated versus non-isolated systems. Okay, so that's just a quick video on really identifying when does conservation momentum apply to isolated systems. And so now we're going to turn our efforts to collisions. Again, I'm not going to make this one big video because that's just going to be, it'll end up being a